Hi everyone, welcome to the Strategic Design Workshop. I'm Helena, I'm going to be the moderator for this presentation. In a second we're going to start, but just a reminder that if you have any questions, please throw them in the chat and we're going to go through and do our best to answer those at the end. So with that, I think we'll get started.
Awesome. Excited to be giving this presentation. I'm Mike Corsetto. I'm the lead technical mentor for 1678. I'm also an engineering manager at a company making robots that clean solar panels. I'm actually I just finished my 17th, going into 18th season in FRC, and started working with 1678 in 2008. And I like to say that for this presentation, Austin and I have leaned heavily on a lot of very talented individuals and teams. Karthik, 254, among the teams that we've leaned on the most for this presentation. So a lot of the credit for the content in this goes to those groups.
Hi, I'm Austin Haddox. I am a strategy, scouting, and mechanical mentor for 1678. I work as a senior data analyst for North Bay School Insurance Authority. I'm going into my 8th year with FRC, and I started mentoring 1678 in 2019.
Awesome. So a couple things we're going to cover in today's presentation. We're going to talk for strategic design. Our focus is going to be about how to utilize the limited resources every team has to be as effective as possible in each of these areas that we're going to cover. So we're going to talk about the preseason and what you can do to leverage that time. We're going to talk about a little bit about drivetrain and mechanism design, electronics and pneumatics, what some keys are there to focus your resources appropriately, and then how to structure your build and competition season for competitive success.
So when it comes to design, it's really important that we don't overcomplicate things. So our golden rule on 1678 is keep it simple, silly. We need to define what our team can do, and we need to design something that's simple and won't break down. And if you ever look at 1678 robots, you'll definitely see a pattern of us focusing on design and functionality over powder coating and painting our robot and making sure it looks pretty.
That is 100% true. So let's talk a little bit about what you can do in the preseason to prepare your team. So for the preseason, one thing that we learned on 1678, and I think was a real turning point for our team, is that the time before kickoff in January isn't just a break to take off and not do anything. That used to be our team's mode of operating for many seasons. And then around the 2012, 2013 mark, right around there, we started operating more on a year-round basis. And a lot of those activities looked like preseason trainings, going to off-season competitions, but a lot of it was also experimentation and trying out new things, new designs. So a lot of the stuff we're going to talk about today might be new to your team, or maybe a couple of topics are new, like there's a new concept or a new mechanism design that you want to investigate. What we encourage teams to do is to try those designs out in the preseason, learn about them. If you have a little bit of padding in your budget, maybe buy a couple of parts and put them together and see if you can make a working mechanism for an off-season robot or just a special project. And a lot of that's going to rely on you learning from past FRC robots and past FRC games. What we find is there tends to be a lot of repetition. So that's a lot of what we're going to be doing in the preseason every year. Even for a team like ours that's been meeting year round for many years now, these concepts are still just as important in our 10th year of doing this as they were the first year we tried working year round.
Yeah, so with some off-season project ideas, try things that you've never tried before, a ball shooter, intakes, elevators, climbers. The kitbot is a really good thing to practice because it's really important that if you plan on using the kitbot, that your team is used to putting it together, since it's really more or less the same every single year. And so if you can get practice putting that together and getting it up and running in a couple days, you're ahead of 80% of teams out there already. And bumpers, of course, are a thing every year, and you don't ever want to wait to the last minute to put them together. So practicing getting everything ready is definitely helpful. For us, we never did a 6-wheel drop center until we practiced it in the off season, and now it's definitely a staple point of our robots. We're currently practicing with swerve drive modules, and hopefully might eventually integrate those, but don't ever put something on your robot that you've never practiced or have any experience with during off season.
Yeah, and a lot of knowing what to practice is going to come from learning game history. So what we find is now that we're really like 30 years deep into FRC, but we're also like 15 years into VEX and 10 years into FTC. So there's a ton of cumulative years of competitive robotics to lean on as far as mechanism design goes. And even within FRC, we have games that repeat similar principles, like climbing challenges from 5 of the last like 10, 11 years have had climbing challenges that look fairly similar. One of the more ironic ones was in 2007, 2011 with tubes, where you literally had similarly sized and shaped tubes that were scored on 3 different peg levels that were almost at the same height as between the 2 games. So there were a ton of lessons learned between those 2 years. I think one of the interesting ones more recently was the 2020 game used a foam ball that was from the same manufacturer as the foam ball we used in 2016. Granted, it was a slightly different skin material, and a slightly different size, but the principles held true. So actually, when 1678 was prototyping early shooters for the 2020 season, we brought out our old 2016 robot and just adjusted some variables and started practicing shots with the 2016 robot, but with the 2020 balls. So there's a lot that you can learn from old games, and being familiar with the games is going to help you have good reference points when the new game comes out, if there's any similarities. But what we talked about just a second ago, you could go one step further and integrate some of the common mechanisms from past games into your preseason design training. So you could say, hey, there's a lot of the past year's games have used elevators. Let's practice designing and maybe even making an elevator, even if it's just going to be strapped to a test bench and go up and down. It at least gives us experience designing the mechanism and building it. So those are some of the values you get from knowing what past games were like.
Yeah, so we're on our golden rule number 2, where just like Mike was saying, look at past years and get those examples of what was successful, and then we can practice those during the off season. This brings us to golden rule number 2, which is steal from the best, invent the rest. We need to look up, what's the best robot from every year? What kind of designs work for shooting a foam ball? I'm not the best robot designer, neither is Mike. I think that we can both agree with that. And we're not going to reinvent the wheel when it comes to designing robots, because these teams have already done this for about 30 years or so. And there are some sneaky, smart strategies that these teams have come up with. So just look at the classic, competitive robots throughout the years. 2056, 973, 971. Actually, they're a little complicated, but 254, 330, rest in peace, 610. We want to look at these sneaky, simple designs that we can copy and make our own versions of. And, just like Robot in 3 Days, we can take advantage of that and use that as our starting point for design.
All right, so I'm going to tackle drivetrain just a little bit. If we go to the next slide, this is a couple of 254 robots, and I like to ask in our in-person presentations what people notice is similar between all the robots, and the answer is not that they're all blue. if you look closely, they're all utilizing a similar drive chassis structure of a West Coast drive. More on a higher level, they're using a tank style drive where they have a set of motors for their left wheels and a set of motors for their right wheels. And that feeds right into golden rule number 3, if you want to go to the next slide, which is use a proven drivetrain. And what this comes down to, I think Austin touched on it just a little while ago, but a key component of utilizing your design resources effectively is using a proven drivetrain that your team is familiar with. Now, for a majority of teams, this is going to be a tank style drivetrain. And actually for a lot of teams, more than maybe teams want to think about, there's a lot of teams that should be using some form of the kitbot drivetrain. And that is because if you use something like the kitbot drivetrain, or just use the kitbot that comes in your registration, you can have a robot, a drive base built in a day, and you can focus your design resources on the scoring elements that are going to be the things that actually get you points in the match. And I think a lot of teams can miss this because designing drivetrains can be kind of a it's an excuse me, it's an alluring thing to do. It's, kind of the sexy thing is make a, who can make the lightest West Coast drivetrain or the lightest swerve drive. But that's actually not really the point of a drive chassis. The point of the drive chassis is to get your scoring mechanisms to the place they need to be. The drivetrain itself is not going to get you very many points in a match. You need the other things to be the best they can be. And so focusing more of your resources onto your scoring mechanisms and keeping your drivetrain simple and sticking with something is not going to take a lot of time to debug and fix is a huge deal. A good counter example to golden rule number 3 is actually 1678's 2008 robots. This is right before I joined. If you want to go to the next slide really quick, this robot was for a game where part of the game was driving around and scoring laps. So actually your drivetrain could score some points this year. But 1678 designed this robot that had 3 wheels, 2 in the front with Ackerman steering, and 1 powered wheel on the back with 4 motors. And if you can't see from the picture, there's 4 motors in the back and a battery strapped above those 4 motors and the 2 gearboxes that those 4 motors go into. So that battery was actually like a foot off the ground, and there was only 1 wheel on the back. So every time this robot took a really hard turn around a corner on the field that year, it would roll over. So it was like the shortest robot, but it was also the tippiest robot because it wasn't a standard drivetrain design. They came up with it that year. It used these potentiometers that weren't very reliable. So there were a lot of problems with this brand new drivetrain they designed. And honestly, they would have scored more points probably if they had just built a standard tank style drive that wasn't going to flip over on them every match and practice with it. But focusing all the attention onto the drivetrain to do this custom drive was not the move. So a proven drivetrain could be a swerve drive if you have a ton of experience with it, and swerve drives are becoming more and more common. And I know people ask about swerve drives all the time. And yes, 1678 has been testing them, and maybe we'll use one in the future if all of our testing pushes us to a point where it's going to be better for autos and in-match driving. But it has to be something that you're familiar with and that you can build in a matter of days rather than a matter of a week or a month.
So when it comes to mechanism geometry, it's really important that we stick to our golden rules and we try to keep it all simple, where we minimize the degrees of freedom. So we don't want a lot of moving parts. That's more things that can break. We want to keep things rigid. We want to keep things structurally sound. And like Mike said about Rare Cab in 2008, having a low center of gravity, having your motors and your battery as low as possible makes it so that your robot's not going to tip over. If your robot's upside down, it's not going to play for the rest of the match. And so we need to make sure that we don't overcomplicate things and plan for that when we're creating our robots, that heavy things go on the bottom. When it comes to symmetry and staying inside the frame perimeter, these are all things to make sure that we're not overcomplicating things, and that also that things don't break outside the field. Robots are ramming into one another. We want to make sure that our intake, whatever we're grabbing that year, doesn't get smashed because a robot was playing defense on us. We need to make sure that what we are putting outside of the frame perimeter isn't going to break when it is out there, and we need to make sure that it's able to come back in when we're not needing to intake something.
So talking a little bit about mechanism movement, and really in FRC, we're provided two primary options for mechanism motion. The first one is utilizing 12-volt DC motors, and the motor game in FRC has actually evolved a lot in the last couple of years. We have some really smart brushless motors on the market now, including the Falcon and the Neo that are head and shoulders above what we had when I was growing up in FRC back in the mid 2000s. But there are quite a few choices for motors that teams have to use. There's a number of different off-the-shelf gearbox options, including planetary gearboxes and spur gearboxes that are also super helpful for mechanism design. So there's not a lot of reason to be doing custom gearboxes in most of your applications because there's so many great off-the-shelf options. But when you're thinking about, do I use a motor or do I use pneumatics, which Austin's going to talk about in the next slide, if you're looking at using a motor, there's a couple things to understand. You do get more power generally with a motor. It depends on which motor you choose, but especially if you're using one of these newer brushless motors, they're packed with power. So the power per weight ratio on a motor is going to be generally a lot higher than what you get through pneumatics. You also have the ability for like variable movements. So for example, in this picture of the 971 robot, those claw, the angle of both the upper and the bottom half of the claw are controlled by their own set of motors. So the claw was able to loop around left and right, but also open and close. And so there were a ton of very sophisticated controls that you could do with that specific robot because they had a motor and gearbox for the upper claw and a motor and gearbox for the lower claw, and they could adjust their shooting angle to very precise angles depending on what tasks they were doing. But the flip side of that is you end up having to put more investment into the software and controls for something like that. Now, granted, a lot of the brushless motors now have internal encoders, which makes those controls a little easier. But if maybe maybe it doesn't need that much power, or you don't have the budget to buy a million Neos and you need to be using a simpler DC motor, you're not a brush DC motor, you're not going to have that internal feedback. So you need to have external sensors that can detect the position of your mechanism. So that adds an additional layer of complexity. And so pneumatics, which I'm going to kick over to Austin, may be a better choice depending on the application that you need power for.
So when it comes to pneumatics, it's really important to know what their application is for. It's really just if you want precise, consistent linear movement, and that is going to be the same every time. So when you are using a motor, you're able to have that variable change, and with pneumatics, you're not going to be able to. But pneumatics are often light, they're small, you can fit them into, right above your wheels, you can fit them in tight spaces that you wouldn't a motor. You don't need a gearbox. However, you're going to need a compressor, you're going to need a bunch of storage tanks, especially depending on how heavily you rely on them. So it's really important to sparingly use pneumatics because teams often run out of air in matches, and you need to wire all the pneumatics, and that's another thing to worry about. But it's also important to not be afraid of pneumatics. I can't tell you how many times I've seen a team to be afraid of using pneumatics and try to figure out how to get that linear movement through motors instead. And it's so much heavier, it's so much harder, and you could have just used your free pistons from Bimba every year to do the same exact thing. So There's definitely cons of both sides, but each one has a very specific application, and if you know how to use it properly, you can definitely come up with some sneaky designs that we're going to talk about later in the presentation.
Awesome. So jumping to another important element of mechanism design, this is in particular for intaking of game elements or intaking of, so intaking of game elements, we call it the acquisition zone. What that really means is what's the effective intake area that your robot has. So the acquisition zone is defined by basically the limits of the extent of how wide you can pick up a game element. So the purpose of increasing the acquisition zone is to decrease the difficulty placed on the driver for acquiring game elements. The most common way that this comes into effect is for things like picking up balls off of the ground. And rather than having a single wheel on a small shaft that you need to line that wheel up right with the ball, and you have a ball's width gap in your bumper for the ball to roll through, instead, teams will have a larger gap in their bumper, or they won't have a gap in their bumper at all. They'll go over the bumper, and they make the intake the width of their robot to allow for a wider acquisition zone. I think this gets missed a lot by teams. I think last 2019 was a good example of this, where we had to pick up both these hatch panels and we had to pick up the orange cargo balls. So 2 different game elements to acquire. That adds the complexity. And so when teams were trying to do both, they sacrificed some of their intake's effective acquisition zone in order to be able to grab both elements with whatever various mechanisms they had. What you found last year especially was teams that sacrificed on the acquisition zone had a much harder time picking up the game element, because the smaller you make the acquisition zone, the more work your driver has to do to get that alignment just right to acquire the game element. And you can imagine that, especially if your robot is 30 feet away from you at an angle and you're driving sideways and you're trying to pick up a ball, if you're not dead on and you have a small acquisition zone, your bumper's going to hit it or you're going to miss it completely. The way I like to think about it is, imagine that you're trying to direct your buddy who has a blindfold on to throw a dart at a dartboard, but you can't view straight on with what your buddy is aiming at. So you're trying to get him to aim, and you don't have any line of sight to where he's throwing the dart at the dartboard. You can imagine that it's going to be it's going to be difficult for you as a third-party observer to aim your friend as they're aiming at the dartboard. And so that's a lot what it's like to have a robot with a small acquisition zone. You're trying to hit this small target with a mechanism that's 30 feet away. So by focusing some design effort into increasing the acquisition zone, you take that burden of responsibility off the driver, and that's going to mean your driver is spending less time chasing game elements around the field and more time picking them up and scoring them.
Yeah, so that brings us to golden rule number 4. So we were just talking about acquisition zone, and there's different kinds of intakes, but especially when we're talking about balls or things that were able to slide off the ground, rolly grabbers. So anything that has a wheel or the urethane tube, anything that's able to spin to grab it and then pull it in. It's really important that we talk about, we touch it, we own it. So anything that, any game piece that our intake touches anywhere in its acquisition zone, it's going and directly into our robot. So it's really important, especially in these games now, that we have a way to pick up if the intake grabs it from the side relative to the robot. So in the picture that we have, that intake was able to grab the ball from the side of the intake. It centered the ball and then brought it back into the shooter. And so this helps increase the effective acquisition zone for our drivers, because we don't need to even grab it head on anymore. We can be a little off-centered, and it's still going to center it for us and bring it into our robot. If we had something similar to 2019, where people used the claws or the Velcro to try to grab the panels, you had to grab it very precisely and then very precisely score it. If you have something that it's able to grab it a little off center, and then as a portion of that mechanism centers it for you, it makes scoring a lot easier. Same as we want to keep our robot simple, it's sometimes a little bit more effective to design something maybe a little bit more complicated to make driving much simpler, because that's definitely the limiting factor in every match.
I think these pictures are up here to demonstrate that. If you go to the next slide too, this is, I think, 10 different 254 robots, and all but one of them have rolly grabbers on them. The only one that doesn't have a rolly grabber is the robot in the bottom right on this slide that's holding the tube. And that robot's the only robot to ever not win the Silicon Valley Regional. So I bring this up every year, not to jab at 254, but to highlight the importance of rolly grabbers. All right, we can go to the next slide. Can I talk about this one, Austin? Is that cool?
You're good.
Awesome. So device robot alignment. I think this is related to acquisition zone, but it's a little bit different. So rather than acquiring the robot, a lot of times there's specific field elements to align to for different tasks. So I'll give a couple of examples here. The scoring towers in 2019 that you put the cargo and the hatch panels on, or the goals that you need to shoot the frisbees in 2013. So it's important when thinking about robot alignment to think about what's going to be the quickest way for me to line my robot up for scoring. And the answer isn't always just slap a vision camera on and use the retroreflective target, because that takes a lot of software overhead to get that right. Sometimes you can design mechanical systems to help with this. So a good example is actually in 2017, there were teams like Team 8, Pally Robotics, that had their gear scoring mechanism on a side-to-side slide. And so when they went up to score a gear on the peg, that was kind of a tight alignment task. And so if their driver was off, they could slide their mechanism over rather than having to back up completely and realign, which a lot of teams had to do if they didn't have that side-to-side sliding mechanism. Another example, if you go to the next slide really quick, in 2013, there's a team I mentored that year, 1662, had these two hooks that they could flip up and engage into the horizontal blue bar that you see in that picture there. And when engaged on that blue bar, that robot was in the perfect position to just shoot all of its frisbees into the goal that was about 15 feet away. So rather than having like a camera system and the driver needing to line up or whatever, the driver would just drive straight into the pole. The robot would just like kind of force its way onto the pole, and then they'd sit there, shoot all 4 discs because they had one shot that was calibrated for that specific position. The picture on the left with 423, similar. They were scoring balls into the 1 and the 2-point goal, and you can see how they just, butt their bumpers right up into the fender there to line up their shot. And a lot of teams shot from the fender that year, even though it wasn't necessarily protected. It was a good place to just index your robot into, and then have a pre-programmed shooter position that would turret over to the right spot and then shoot the balls into the goal. So this whole like alignment, how do we quickly line up is an important thing to think about. Actually, another really good example that I don't have a picture of is in 2011. We had these mini bots that we had to launch up these metal poles, and some teams that kind of thought through the problem a little bit more had these large kind of, we called them like whale tail funnels that were on the front of the launcher mechanism. that they would deploy out and ram into the pole. And so if they were off to the left or the right by like 6 or 12 inches, the funnel would center the robot's launch mechanism onto the pole, and then the mini bot would be fired effectively right onto the pole. So that's another example of alignment, and that's actually kind of like a mix of alignment and acquisition zone, because it makes the driver's job a lot easier, right? But thinking about, okay, we need to acquire the ball with the wide acquisition zone, but then we also need to be able to reliably score our game element by having a effective alignment strategy that doesn't just, kick the problem over to the software students every time, because that's not going to be the right answer 100% of the time. Yes, sometimes you need to use vision. We use the limelight on 1678 very regularly, but that's not always going to be the answer. And it's important to recognize where you can design those in mechanically versus where you need to rely on software.
Yeah, I
Cool.
think that a good example for this in past years is always for scoring, that there's always fixed points on the field that you're going to be able to base your alignment off of. There's normally a square field. In 2014, 254 would always butt up against the low goal, which was just a cube, and so that would be the perfect shot for them. They could shoot from other places, but they knew the point of this is that no matter what you do, you're going to grab it. So, or you're going to score just by no driving of you, or no error from the driver is going to be able to change this, because you have a fixed element of the field, or a fixed part on one of the elements that you're able to line up with. I saw teams in this last year, 2020, line up against the I forgot what it was called, the giant tubes in the center, and they were able to effectively do a 3/4 shot into the high goal with lining up, and no vision was ever required. So it's always important to realize what you're able to line up with and what you're trying to line up to. So when it comes to electrical and pneumatics, this can go wrong very quickly. It's really important to stay organized, because if you don't, you just have a bunch of random wires going everywhere, and you're not really knowing what's going to what. You're not able to diagnose problems very easily. So it's really important that we spend the time to do it right, to make sure that if you want to put in the effort, maybe have things color coded, have things going through channels together that have similar uses or similar locations, so that you're able to quickly diagnose all the wires at once, and it keeps it clear if there's any mechanical or electrical or pneumatic issues of any kind that you need to diagnose, you know where to diagnose them. A really good example of this is in 2019, we had a lot of electrical issues, and it's really important to understand where the problems are coming from. We spent the entire season diagnosing problems that made us die on the field, and we never solved those problems. And so it definitely led to issues with our autos, with reliability, and keeping things straightforward, simple, is definitely an easier way to make sure that everything is going according to plan. And if things are going wrong, it's the easiest way to fix it, because you're able to look at what's going on. Don't make things harder for yourself just because it's easier in the moment. And
talking about the other side of this coin, programming, when we're thinking about strategic design, and especially what you can do in the preseason with your team specifically, look at your programming abilities and try to like pack your toolkit with a couple of basics that are going to be important for the upcoming season. The first of these is the ability to have a precision autonomous driving routine. Outside of 2019 that had Sandstorm with like the option to drive manually in auto, every year has had a fully autonomous portion of the match since like 2003 or 4 or something like that. What I find way too often is teams are not prepared to have their robots drive in autonomous. And so, and even if they are prepared for some driving, they're doing a lot of the research and development on how to do that during the build season. And honestly, you don't want to spend your programming time on that sort of challenge. So what I encourage teams to do is take an old robot and get really good at the basic skills of, I want to draw a path that our robot's going to take, and I want it to follow that path. And that's something that you can build up that toolkit in advance of kickoff. Same thing goes for vision alignment. This has become more and more of a standard element of every year. There's always vision targets that you can utilize. Either you need to turn your robot towards the target, sometimes you need to drive at the target or index off the target in some way. So being familiar with the vision system that works for your team, that you have access to and practice with, is another great thing to have ready in your toolkit. And then knowing how to program PID controllers for precise positioning of mechanisms. I'm thinking of things like, arms or elevators that need to go up to various different heights. And how do you control that mechanism to hit those different marks? That's going to utilize a closed feedback loop controller like a PID loop, or there's stock code available on Talons and on Spark Maxes in the Falcon 500 that you can use, but being familiar with those things in advance of the season is also going to be a huge benefit, not only to your programming team, but if your mechanical team knows that your software team is ready to control something like an elevator, your mechanical team could be more confident in building the mechanism like that. And then the same thing goes for, we call it like a bang bang controller. It's a different type of closed loop controller that's a little bit simpler, but teams will utilize often for their shooter wheels, for games like 2020 with the foam balls. So being familiar with that method of control, having the ability to quickly pull these various functions out of your toolkit and utilize them in the upcoming season is a huge benefit, and it takes out a lot of time. And again, time is like the thing that we're trying to optimize for in all this stuff. And we're going to be talking a little bit more later about why some of the other decisions we make are optimized for time. But having these programming skills in your toolkit going into a season are going to save you a lot of time and are going to allow you to build a more effective robot.
Yeah, so in build season, we're going to talk about why it's important to have an accelerated schedule, why we need to finish things early, when setting a schedule, it's important to set our standards so that we that even if you miss, you have the time to succeed, even if you're a little bit off. And people always assume that, especially with there being no bag anymore, that you have infinite amount of time. You don't. It always goes faster than you think. Every single year, the team's talking about how it's week 6. I'm like, what are you talking about? It's week 6. So it definitely happens to all of us, but these schedules keep us on track, and it keeps our development moving forward. So in
all right,
week
so
one, sorry,
you're gonna go through this? Go for it. Yeah, go.
Okay, sorry. So in week 1, it's kickoff, obviously. So we focus on understanding the game in days 1 and 3, and we all meet together and we talk about the possible designs and possible challenges that we're going to come across. In day 3, we already have decided what kind of drivetrain we're going with, and we're making sure that our drive-based design is solidified. Moving forward to the end of week 2, we're prototyping. We're making sure that our drive base electrical layout is solidified, that we have a plan moving forward. We know where sensors are going, we know where motors are going, we know where the battery is going. We need to make sure that we have our drivetrain done and ready to drive, and we need to start writing code for the mechanisms that we've decided that we're going to move into through our prototyping.
All right, so let's talk a little bit more about that brainstorming session in days 1 through 3. This has been probably, for me, one of the most important parts of this whole presentation, is talking about how you handle that beginning of the season. Now, granted, 2021 is going to be an interesting year because we're not getting a brand new game. First has already told us that. It's going to be a very similar, if not identical, game to 2020. But with new challenges involved, and Frank talked about a little bit that in the beginning of the workshop session yesterday. But in a typical year, the kickoff brainstorming weekend is the most important weekend of your entire season, and how you handle that weekend is going to set the course for your whole season as a team. On 1678, we have 3 specific steps that we go through to structure our brainstorming weekend of kickoff in order to be successful for the rest of the year. Step 1 in that process is reading the rules, and we believe that this is a process that every team member needs to go through. And we have a rules test that every student participates in at the beginning of the year, and at the beginning of kickoff. So like probably within a couple hours of the game being released, our leadership team has developed a Google Forms rules test, and then that's distributed to all of our students who have been reading the rules since kickoff happened. And then by the lunch on our first day of kickoff day, we have all of our students who have passed the rules test, more or less. We also publish this rules test, so if you're interested in a rules test that you can distribute to your team, we publish it right when it's available on kickoff morning. So feel free to check our team's social media or Chief Delphi on kickoff morning, because we publish this every year. And then step 2, which usually takes from Saturday afternoon until Sunday morning, is answering the what questions. So what is our strategy? What will the robot do? We'll talk about that a little bit more in the next slide. And then answering the how questions is usually Saturday or Sunday afternoon through Monday morning. Usually Monday is a holiday right after kickoff in California. And the how questions are there to ask, how will the robot carry out this function? So we've talked about what we need to do, kind of that strategy questions of like, what's the core strategy of what we're trying to accomplish with the robot? And then the how is going to be a lot of the ideas for how you accomplish that strategy.
Yeah, so just like what Mike was saying, the whats are, what are we going to do? What are the ways to score? What is each thing worth? What is the difficulty? And we assign values of design points. This is from Karthik, that nothing needs, or we need to focus on making things as simple as possible. And so everything that's not necessarily for the game, it's really important that you guys cut that out, because every single thing takes time in your season, and every single thing that you're able to cross off this what list is another thing that you don't need to spend precious time focusing on how you can accomplish that. So every time that you decide to specialize or to focus on one point of the game as your main design of the robot, you guys should be celebrating that, because it's not just something that that is the right thing to do because someone else is doing it. It's what you guys have decided to meet your goals this year, and you decided that you're not going to waste time, energy, and resources on that. A perfect example of this is 2910 or even 973 in 2019. Neither team decided to go for the highest level of the rocket, and both teams easily could have won the world championships. 973 was the world championship alliance leader, and they decided that it wasn't worth the extra time, weight, effort to design something that made it to the highest level, and they were able to use those resources to better focus on what they decided to do. Mike's going to talk about how we decide we're going to do something.
Yeah, so talking about the hows, so once you have a list of the what's, which is every functional requirement for the robot, and this goes down to the level of we need to be able to drive, we need to be able to drive over this bump. Like those are the things that you want to put down on your what's list, in addition to we need to be able to score at this level, we need to be able to pick up a ball from the ground. Those are all what's. But then we go to the how section. And on kickoff weekend, when we're talking about the hows, we break out into smaller groups, and every group is looking at this list of things that are going to be required for a robot this year. And we talk about what sort of mechanism designs could carry out each of those functions. So maybe the idea of scoring a ball into a goal that's 8 feet off the ground is very similar to what we did in 2016. So we have an idea of what that could look like, and we can draw that out, and we could be like, what if we took a lot of the lessons learned from our 2016 robot and put it on our 2020 robot? And you come up with these ideas, and the big thing here is being able to effectively communicate your mechanism designs through quick sketches and maybe a quick Crayola CAD here or there, something that's easy to put together really quickly because time is of the essence this weekend, and then that you can communicate with the rest of the group. And we actually have each of our small groups of students present their ideas to the rest of the team on a whiteboard and or projector. And then keeping things to scale is going to be really important here. One of the best examples I have of this is back when we were sharing our how ideas in 2014. That was the year of the big exercise balls that were like, I think they were 25 inches in diameter or something. They were very large. And I remember seeing a sketch one of the groups of students on our team put together and presented to the rest of the group. And they had a sketch of a robot, and there were like 3 little, what were supposed to be the exercise balls, like stored in the bottom of the robot. And you could tell right away that if each of those balls was actually 25 inches, this robot was going to be massive and completely outside of the rules of the game that year. And so it's important when you're thinking through your design ideas that you're keeping things to scale, you're keeping in mind what your extents of the robot, the maximum extents of the robots are for that season, given the rules. So that's how we kind of talk about the hows. And the goal for the hows section is to have a list of mechanisms that you want to pursue, either going straight to design or going into your prototyping with your prototyping groups in order to validate the ideas that are presented. And then I think we got to skip this one. This one's kind of out of place, and Austin can talk about week 1.
Yeah, we talked about week 1 already. Yeah. So in week 2, we have our drivetrain finished. We have the entire thing wired, and we're able to test driving. In starting day 8 through mid of week 3, we're focusing on putting our initial versions of our mechanisms together. We never distinguish the prototype and the mechanism. It's just all kind of one thing together. We make iterative designs throughout the season, and so our prototypes get tested, and then we fix them, and then we test them again, and we fix them. And throughout that process, as we're adding functionality, we're adding rigidity, our programmers are making sure that we're able to better test it. So initially it's with a simple test board with a button, and then we use a joystick, and then we have it on the a practice robot, and then we have it on the robot itself. And then we start integrating these mechanisms together. And like I said, we start assembling this on a robot with our initial code base.
All right, and that takes us right into day 29, where so by the end of the 4th full week, we try to have a robot quote unquote finished. But that is not the end of the development cycle. And I think John JVN is a great person to listen to when it comes to iterative design. He has a lot of great insight on this exact topic. But what we try to emphasize is the testing and especially the breaking process of our robot, and then fixing those breaks, and then implementing those and seeing if it breaks again, and if it breaks in a different way that we can fix. The goal with this is golden rule number 5, which I say is fail faster. This idea of when you go to a competition and you see a robot that is performing at a higher level than yours, maybe because it's more reliable or it's scoring more points per match, it's probably not because the people that built that robot are perfect and they have perfect insight, and it's just they spent the same amount of time as you. It's just they came up with a wildly more amazing robot. I think what happens more often than not, especially in something like FRC where it's a brand new game every year, is everybody's getting this game brand new. The difference is how fast you're able to fail and how quickly you can learn from those lessons and implement those lessons. So maybe a team that's performing better on the field had more failures in their shop that they were able to identify, and they were able to through fixing their robot through driver practice. And so they don't have the same problems that your robot might have on the field because you haven't discovered all the problems yet. So that failing faster mentality, this idea of, I know even though we finished a robot, it sucks, and we need to figure out how it sucks, and we can only do that by testing. And then that driver practice really comes into play too, because what we find is a robot that may have been designed fairly well can still lose a match because it doesn't have a familiar drive team behind it. And so this idea of driver practice is not just for the drivers, it's also for fleshing out your robot problems, and try to combine the two. Try to do as many driver practice sessions as you can and take notes during those driver practice sessions about what breaks on the robot, so your design team can be fixing the robot problems while your drive team is getting practice with the robot. And both of those are feeding into each other to have a successful machine.
So specifically when it comes to no bag, we're short on time, so I'm going to rush through this. Same as with the normal season, you don't have as much time as you think, just because there's not a specific date that you need to be done by besides your competition. You're always under the gun when it comes to time, especially because you need to have that strict schedule for yourself, as well as this is an opportunity to continually work on your robot after that normal 6-week season, because other teams aren't going to stop. And so it's important that you don't as well, because they're just going to leave you behind.
Yeah, and then another thing, we talked a lot about how important driver practice is, but it's really important to also understand how the game is going to play out. So one thing we do on 1678 is we watch other competitions every year. We do, you can see the picture there, we do a pancake party every year where our mentors and students make pancakes for each other while we watch matches early in the morning, usually like the first week of competitions. And just do your research, like learn about how the game's playing out, read Chief Delphi, watch all the different amazing first content that's out there in the community, and get familiar with how the game is playing out, because the more you understand how the game is played, the more successful you're going to be out in the field.
Yeah, so just you know, as a summary, with preseason, it's really important that you use this to prepare your team for the season. When it comes to drive base, Stay with simple, proven designs when it comes to mechanisms. Don't try to overcomplicate things. Try to keep things simple. When possible, stay structural, and with electrical and pneumatics. Don't overcomplicate things, and make sure that things are organized. Build season and competition season, don't underestimate the amount of effort that things take, and make sure that you have enough time to complete these.
Great. Just resources, Compass Alliance, Chief Delphi. Hopefully you've seen them before, but if not, check them out. Yeah. And Helena, do we have any questions?
Yeah, we have one question in the chat. It says, what are your thoughts on Swerve with proven COTS solutions?
So I've been really impressed with the quality of the COTS swerves that are on the market right now. When thinking about Swerve, like 1678 has been testing with a couple different off-the-shelf solutions. I'm going to be honest, I don't know at this point why, especially if you're a team that's never done Swerve before, but even if you're a team that has done Swerve before, I'm not sure why you would ever build your own at this point, because there's so many great off-the-shelf makers of Swerve drives now that do 98% of what you need a Swerve drive to do, and you can buy it and forget it. That, you know, I think off the shelf is the way to go for Swerve drives. I'm interested in what Austin thinks about that.
No, absolutely. I don't think that we're ever going to put in the time to design and test our own, because we're always going to just buy one if we ever decide that, because they're already doing that iterative design on their own. Patrick from 2910 is doing a great job with his, and he's been making new iterative designs every single year, and I'm very excited to see his new models. But I definitely think that the whole thing in FRC, when it comes to in the game or in the season, or even prepping for the season, it's all about time, and that's the most expensive resource you have. And so, even for teams that are strapped for cash, buying these resources or using COTS parts as much as possible saves so much time and effort.
Mm-hmm.
Great, thank you guys.
Absolutely.
And with that, I think we're pretty much out of time. Thank you guys so much for watching, and thank you to the presenters for presenting. And make sure to tune in to the next workshops that are going to be on these live streams. Thank you guys.
Awesome. Thanks, guys.
Thank you. Bye.